Alright, g'day, I'm Mitchell, and this is my high performance computing parallel milestone presentation. So first, a little bit about my problem. I'm doing polynomial multiplication using a discrete Fourier transform. So one thing we can do with the discrete Fourier transform is a multi-point evaluation. So let's write out the coefficient, our polynomial as a coefficient vector. The discrete Fourier transform will compute an evaluation at n different points. We can also do an interpolation where we've got what the polynomial is when we evaluate it at a bunch of points, and then we get back to the coefficients. So using both of these, we can produce a multiplication algorithm, which is fast in practice, as well as asymptotically pretty fast. So what we do is we evaluate our polynomial using the DFT at all of these powers of a primitive nth root of unity. And that just introduces some nice symmetry into our problem. We evaluate both of the operand polynomials. Now we've got these vectors of what they are evaluated at different points. If we multiply those together pointwise, that's actually going to be the same as the multi-point evaluation of their product at all of those points. So we'll just interpolate the product from this array C. And so this is an n log n algorithm, whereas the classical polynomial multiplication is quadratic. So there's two algorithms which do this transform we're interested in. One of them, also, no, not one of them, both of them are in place, which is awesome, but I guess the cost of us getting them in place is now introduces permutations into the array as they work through it. They swap values around. So what's nice about these two algorithms is they're dual in the sense that if we do FFT2 to go forwards, that is to do the multi-point evaluation, then we do FFT1 to come back using interpolation, those permutations cancel each other out, which is fantastic because we can save a bit of work. So let's have a look at my serial code performance. At the biggest size, when the polynomials I'm multiplying together have size 2 to the power of 15, it's taking me a little over 10 milliseconds per multiplication on average. And this is a little bit faster than the Maple computer algebra system running on my computer, much my home machine does. So I think that's pretty cool. But we can make it better. I ran through the profiler, and unsurprisingly, most of the time it's just spent doing arithmetic. So if we can make this faster, like these couple of functions, we should be able to get a huge speed up in the whole thing. So I first tried to do some AVX stuff. Unfortunately, there's no modular instructions or instructions to find remainders. So whenever I'm doing my additions, subtractions, and multiplications, I'm working over a finite field. So I'm working modulo a prime. 2 to the power of 16 plus 1 is my prime. And I need to be able to reduce things modulo that. I found a paper which has an addition algorithm which I'm using. And I used some ideas from that and some other cool ideas to write my own addition and subtraction algorithm, or subtraction and multiplication algorithms. Let me walk you through my multiplication algorithm, like the key idea. So what we want to do is compute the product with addition and subtraction. Once I've done the addition and subtraction, I just need to add or subtract p at most once to get it to the normal form. But with multiplication, that's not the case. We'd have to do a lot more operations. And so to avoid an iterative algorithm, which could be expensive, what we can do is just notice that because my prime is 2 to the 16 plus 1, it's really close to a power of 2. So what we can do is consider the Euclidean division of the product by 2 to the power of 16 and recover the quotient and remainder. Now, if I just add and subtract the quotient, I can get 2 to the 16 plus 1 to appear again. Then when I reduce all of this mod 2 to the 16 plus 1, I'm just going to be left with r minus q. So what's nice about this is that r and q, the remainder and quotient, are really easy for us to compute because the quotient is just the product bit shifted right 16 places, and the remainder is just the least significant 16 bits, which we can recover using a mask. By inlining a couple of the recursive calls, I could make these for loops guaranteed to be big enough that I could use my vector operations inside of there. So what I did is I did that. I used AVX in all of the for loops in these algorithms and also in the multiplication algorithm, which multiplies the vectors together at one point. And then that gave me a pretty good speed up. And the next thing I did was unrolled all the loops in those inlined base cases. And there was actually a lot of symmetry there, so I could use AVX in the base case as well. So here's what the performance is looking like. Before I had done AVX stuff in those inlined base cases, I was getting up to I guess, a little over 2.8 times speed up over the serial implementation when I was using polynomials of size to the power of 15. But then once I'd inlined everything, I was up to a 3.2 times speed up over my serial code, which actually was looking at about 3.2 milliseconds on average for each multiplication, which is a lot faster than Maple now, but we can do even better. The next thing I did was put some thread level parallelism in with OpenMP. The first idea was, I guess, the most obvious one, just run the loop iterations in parallel. This was actually way slower than the serial implementation. Like, it was shocking. I think I've got some ideas for why that might have been. First, the loop bodies are really, really fast. So I guess just doing threads could have introduced some overhead, which dwarfed the cost of the loop bodies. And another thing is, each iteration of the for loop has to work with 3 different arrays. And so that could introduce some serious cache or memory bandwidth problems. So I guess my next idea was, why don't I just do the recursive calls in parallel? But there can be as many as 31 recursive calls that each FFT algorithm makes. And I only have 8 physical cores to work with. So my idea was, what if we just do like the topmost K recursive calls in parallel? So here, that would look like, say, doing everything up to and including one of the lines in parallel. So we could do depth 3, and so that would mean running all of this stuff in parallel, and then each of these calls its children in serial with its recursive calls. It turned out that depth 2 was the fastest, which surprised me because I've got 8 cores and I'm only using 4 threads at depth 2, whereas I'd be using 8 threads at depth 3. So, yeah, I guess that's likely just another memory bandwidth thing. Like, my AVX things are able to chug things through the CPU so much faster than memory. I imagine it's memory throughput that's really slowing this down and keeping me at depth 2 only using 4 physical cores. I also implemented a minimum size, so once we get down to small enough recursive cases, like, don't bother doing any parallelization because it's going to be slower. So once I'd done that with my OpenMP, I've plotted another chart. So this blue line was my best AVX only implementation that we looked at earlier. And now this orange line is that plus the OpenMP stuff. And so we get up to more than a 4 times speed up in the best case over my serial code. And now I'm down to less than 2.4 milliseconds per multiplication of polynomials of degree 2 to the power of 15. This is really fast because Maple is about 13 milliseconds. So yeah, I was very happy with that. I think it went great, the project. Something I think could have been better was picking a better problem. My problem has a maximum size for the polynomials I can work with, which is 2 to the power of 15, just because the algorithms only work when the size of the polynomials divides the prime minus 1. Although I did get to do some really cool non-trivial AVX stuff when I was writing the vector modulo arithmetic stuff. I wrote some pretty funky code for that. Definitely go check it out. It's pretty cool. I was just blown away by how fast AVX is. We got almost I think it was a 3.2 times speed up. That's almost 4 times, which is crazy because I'm packing 4 integers into each vector. So it was really, really effective. I'm more than 5 times faster than Maple, with like a little asterisk. I do have to decide. Maple, has to decide what kernel code to use at runtime after it interprets some user code, which is going to be pretty expensive. And I cheat a little bit because I'm only working with 1 prime. Maple's got to work for any prime. So an extension for my project could be to stop cheating, I guess, if you can call it that. I don't think it's really cheating, but I guess make the problem a bit broader and implementing a modular multiplication algorithm that works for any prime. Thank you.